Welcome back. So in the last video, we did a bit of analysis how to characterize an LTI system. We used the property of linearity, then we used the property of time invariance, and we came up with a characterization of an LTI system. And an important part of this characterization was that we we characterized our continuous LTI system by its impulse response, right? Through the convolution integral. Right? So effectively what it means, it's very interesting. It means, we'll try to show it graphically. It means I have a system T which has a system property T. To this system you are feeding x of t and you are interested in knowing what the response of this system is going to be. Right? This is an LTI system, huh? So whenever I use t, it means an LTI system. I don't need to write it every time. So you have an LTI system, you are giving some arbitrary input x of t, and you are expecting some output, right? And the normal sequence of operation would have been okay, you apply the signal to your system, you see how your system behaves, and you record the output, then you will be out, then you will get the output. But the beauty of convolution integral is that it tells you this is response. Yeah, you can say for the same system, you apply a shifted impulse and you will get an impulse response something like this. Then from this information we can actually calculate y of t. So you don't need to apply this x of t to your system. This is what your integral says. Y of t is x of tau, which is your input. Then ht minus tau. This is basically the response of the system to the impulse signal. So if you know the response of your system to the impulse signal, then that response can be used to determine the response of the system to any arbitrary signal x of t. Now you may ask that why do we need this? Why can't we just simply feed our signal x of t to the system and just record the response? But the thing is, x of t can have varying properties. X of t is any arbitrary signal. Now it may happen that it's a very complex signal. It may have sinusoids, it may have exponentials. It may happen that this signal is coming in real time, so you don't know the actual statistics of this signal. It may happen that this signal is corrupted. There are various scenarios, right? So instead of directly feeding this signal to your system and finding the response, you have an alternate method through the convolution integral, wherein you are applying an impulse signal to your system. Now, impulse signal, it is defined. You know the properties of your impulse signal. You know that it has to satisfy these two conditions, this and this. So you have studied this particular signal, and obviously to calculate its response, it will be much easier than some arbitrary signal x of t. Right? So this is the importance of this integral. It allows you to calculate, to determine, to compute the output of your system to any arbitrary signal using the response of the system to the impulse signal. Right? So this is one important point, that LTI system, it is actually completely characterized by its impulse response. Means you don't need to feed your actual input to your system. Just see what the response of your system is to the impulse signal and then use the convolution integral, and that is sufficient, that is sufficient to compute, to calculate the response of your system to the signal x of t. Fine. So this is a very important operation in in signals and systems. In fact, it is one of the 4 core algorithms that drives the DSP. We have convolution, then we have 3 more jo aap aage padhenge. FIR is there, IIR is there, and FFT is there. Anyways, you don't need to go there, but it is very important. So let's analyze it a bit more and just try to see what its properties are. So first of all, the representation. How do we represent the convolution integral? So integral as such is represented like this. It is a integral between the limits minus infinity to plus infinity. You have the actual signal x of tau, then you have the shifted impulse response like this, and it is equivalent to, mathematically we use a symbolic representation, this a strict, fine. So we say we have x and xt, ht, they convolve, and the way we calculate is using this integral. So like I said, this is commonly referred to as an what we call convolution integral, right? So you can say the response of the system, that is y of t, is actually the convolution of the input with the impulse response h of t, right? So one of the important properties is that it is commutative. So if you have y of t as a convolution of x of t, h of t, and it is actually equal to this integral minus infinity to plus infinity x of tau h t minus tau. Please remember tau is a dummy variable. It again is physically, it again means it again is a variable that specifies time. So if I do a bit of substitution here, say I put another variable, say tau 1 equal to t minus tau, fine. Then what will happen to the limits as tau tends to infinity? So tau 1 will tend to t minus infinity to t minus infinity, which is minus infinity, because if you subtract from some finite quantity minus infinity, so it will be minus infinity. And as tau tends to minus infinity, tau 1 tends to t minus minus infinity, that is t plus infinity, so that is infinity. Also you can say in this integral, so we have put tau 1 is equal, maybe I should have written here, it means then tau is equivalent to t minus tau 1, which implies d tau is equivalent to minus d tau 1. Okay. So with these, this integral, it will appear like this. So it will be infinity to minus infinity x of, so tau ke badle, tau ke badle t minus tau 1, then for t minus tau we have tau 1, then for d tau we have minus d tau 1, and the limits will change because as tau tends to minus infinity, tau 1 tends to infinity, so the limits change from infinity to minus infinity. So I will do a little rearranging, minus bahar nikalte hain, so it will be infinity to minus infinity x of t minus tau 1 h of tau 1 d of tau 1. So if I include this negative with the limits, so it will turn out to be, so limits will change from minus infinity to plus infinity. Then I will slightly rearrange. I will first write h tau 1, then xt minus tau 1 d tau 1, which is equivalent to h of t convolution x of t. Okay. So this operator, it is commutative, fine. Just like your addition multiplication, convolution is also commutative, fine. So convolution is commutative, that is to say y of t is equivalent to x of t convolved with h of t. This is the same thing as h of t convolved with x of t. So the order doesn't matter, right? आप x of t पहले लिखिए या h of t. And in terms of integral, it means that these two integrals d tau, they are the same. Fine. So you can use either of these. Sometimes it becomes easier to calculate this integral, sometimes it becomes easier to calculate this kind of an integral. Fine. So this is the commutative property. So we'll be using this in solving the examples. So I discussed it here. We'll be discussing the convolution properties separately. Fine. Like it is also distributive. Fine. Similarly, it is associative. So these are three properties. As an operator, convolution coefficient, it is a mathematical operator, by the way, so it will follow these three properties, right? Then when we use this convolution to characterize our system, then we will discuss other properties like causality, what has causality to do with the convolution, what has stability to do with the convolution, that again we will take separately. But as an operator, as a mathematical operator, it is commutative, associative, as well as distributive. Fine. So चलिए वो properties मैं यहीं पे लिखता हूँ, because so this is the commutative prop, so that it kind of completes this thing. So it is commutative. So similarly it will be distributive. So it means if you have a signal x of t and you convolve it with like something like this, you have h1t plus h2t. So this is actually equivalent to this thing. And this is the distributive property. Then again we have the associative property of the operator, that is xt convolved with h1t convolution h2t. This is the same thing as x of t convolved with h1t convolved with h2t. Right? So these are three properties treating convolution as a mathematical operator. And when we use it to characterize a system, those properties we will discuss separately. Again, before we solve any problems and before we further go deep into the convolution, let's try to analyze the integral as such. So we have, okay, I will start a new board here. Okay, so this is my integral. Fine, this is the equation, this is the operation that defines my system, my LTI system. This is the mathematical operator representation. Then as an integral, it will be from minus infinity to plus infinity, x of t, h of t tau. Okay, fine. So, sorry, it will be this, just a second. H of tau. Fine. So once you compute this integral, when you have to calculate this integral, it involves certain quantities. First quantity is x of tau. It is basically your input signal, so no great deal here. Then we have the quantity h of t minus tau. Fine. So maybe I should write it here, a bit of elaboration, that whenever you have to compute this integral that will define the output of your continuous time LTI system, you have to get this quantity t minus tau. Fine. लेकिन हमारा जो इसमें इंटीग्रल में जो मेन टाइम वेरिएबल है with respect to which we are integrating, it is basically tau. So I can express this as h of minus tau minus t. Okay. And this is basically a combination of two operations. So this basically means that the impulse response h of tau is folded, yeah, time reversed to get h of minus tau, fine, and then time shifted by t to get h of minus tau minus t, which basically is h of t minus tau. Fine. So this means, if you remember when we did the basic operations of the signal, I had told you that time these basic operations, these are very important. Although individually they may seem simple, but जो आपके complex operations, like convolution is a complex operation, right? These complex operations are actually being computed in terms of these simple operations. अब आप खुद यहाँ पे देख सकते हैं कि to get this you are actually performing two basic operations on the signal. Mathematically तो ठीक है, you can just have x of tau, h of t minus tau. It will be some function, just calculate the integral, आपके पास result आएगा. But you need to have a physical significance of the things, and the best way to do so is to have a what happens to the signal, what happens graphically to the signal, that will give you a better understanding. So what I'm doing here, I'm performing two basic operations on this impulse response. First, I'm time reversing it, which means I'm folding it about the origin, and then I am time shifting it by some amount t. Fine, this is the first step. Fine. Then second step is you just compute the product, just multiply your input signal x of tau with this value with the time reversed shifted version of your impulse response. And then third step, finally calculate the integral. Once you have got the product, then calculate the integral this with respect to tau. Right? And this has to be repeated because the range is from minus infinity to infinity. Obviously it will depend upon the particular case. Okay, what is that limit जिसमें आपका signal define है. Right? We'll stop this video here. Next video we will do a couple of examples. We'll be following this particular process to calculate our continuous time convolution integrals.